Hello everyone. Today we're going to talk about outbreak and cluster investigation. It is one of the most exciting and challenging part of the course. This is a core function of public health. In fact, about 10 cents of every dollar spent by state health agencies goes toward investigating outbreaks, clusters, responding to natural disasters. Why do we study outbreaks? Three main reasons, right? The first, we need to quickly figure out what's causing the problem and so we can stop it. Second, outbreaks often give us clues that lead to bigger discoveries. And third, the public demands answers. When people think there is a disease outbreak or a cancer disaster, they want to know what's happening and what are we doing about it. So let's dive in. First, what exactly is an outbreak? An outbreak is an epidemic limited to a localized increase in disease, usually infectious. Think of it as a small, contained epidemic. Now let me give you a classic example. Toxic shock syndrome in 1979 and 1980. Starting in October 1979, 5 states' health departments reported unusual cases to CDC. The patient has high fever, vomiting, and diarrhea, then progression to shock. The case fatal rate was 13%. That means 1 out of every 8 patients die. That was very high. The CDC investigated 55 cases of toxic shock syndrome across the country and discovered that high absorbency tampon was linked to illness. The bacteria could grow in those tampons and produce a harmful toxin that caused the condition. Health officials advise people to avoid high absorbency tampon and change the tampon regularly. The Relay brand was removed from store and other manufacturers reduced the absorbency of their product. As a result, cases of toxic shock syndrome dropped significantly. However, cases have started to increase again in recent years, and the experts are not completely sure why. This shows that the disease surveillance and outbreak investigation are still ongoing efforts and remains important for protecting public health. Let's talk about clusters. A cluster is an aggregation of relatively uncommon events in space and time that people perceive as greater than expected. Notice the word perceive. That is important. Cluster can be real or perceived. There are 4 types. Spatial clusters, more cases in some places than the other. Temporal clusters, more cases at certain time. Space-time cluster, both. And time cohort cluster, a group with shared characteristics like occupation. Here is a cautionary tale from Edmonton, Alberta. Initial data suggested a cancer disease for most sites. Media coverage was intense. People were terrified. Property value in one affected community dropped by 5%. That is real economic harm. But then something happened. Several months later, researchers reanalyzed the data and found that there was an error in the population figure. Then they had been using the wrong denominator. After the correction, only one elevation remained: bladder cancer in women. So the cluster was mostly an illusion, but the damage was already done. This teaches us even perceived cluster can cause real harm, and we have to respond with compassion and good science. Outbreaks and clusters are different in important way. Let me walk you through this comparison table. So outbreaks are usually infectious. Salmonella, hepatitis A, that kind of thing, right? The agent is a transmissible microorganism. So that is bacterium or virus. The time frame is short, usually in days or weeks. Um, Effect estimates are moderate or too large, meaning that if something causes an outbreak, the relative risk is often 10, 20, or even 100. Exposure period is acute, hours or days. Lab confirmation is common, and the most common study design is a retrospective cohort study. Clusters are different. Usually they are non-infectious, like cancer, birth defect, that kind of thing. The etiologic agent is often unknown or involved with multiple factors. Time frame is longer, usually is weeks or months, sometimes even years. Effect estimates are weak and moderate, often a relative risk under 3. So exposure is chronic, years or even decades. Lab confirmation is less common. And most common study design is case control. So a salmonella outbreak from a restaurant, that is very different from a possible cancer cluster in a neighborhood. So you need to investigate them differently. Outbreaks come in 3 main types. The first type is the common source epidemic. This happens when a group of susceptible people are exposed to a common source of pathogen, usually at the same time. When exposure is simultaneous, it is called a point source epidemic. The epidemic curve has a sharp upslope and more gentle downslope. Look at Shingilla sonic break from Iowa in 2001. That tight cluster of cases all within a few days tells you that it was a common source. A contaminated water supply is another example. The second type is the propagative epidemics. Here the agent spread from person to person. The epidemic curve is a gentle upslope and a deeper tail, sometimes with a second group of cases later. The measles outbreak in Anchorage in 1999 is a good example. You can see the wave move through the population. Third, mixed epidemic. This starts as a common source outbreak, then spreads person to person. Many foodborne pathogens work this way. People ate contaminated food at a picnic, then go home and infect their families. So you get initial spike followed by a secondary wave. Here are the 10 key steps in an outbreak investigation. This is your roadmap. Let me read them quickly. First, determine existence of epidemic. Confirm diagnosis. Define a case and estimate number of cases. Orient data in time, place, and person. Determine who is at risk. Develop an explanatory hypothesis. Compare hypothesis with established facts. Plan and execute a more systematic study. Prepare a written report and execute control and prevention measures. These steps are not always linear, right? Often you're doing several at once. You might start control measure before you have all the answer. but this framework keeps you organized. The multi-state Somalia oceans break is a good example. Investigators follow those steps, trace the source to something unexpected, which is marijuana use. People who use marijuana were much more likely to get sick. Without a systematic process, they may have blamed the food or missed the real cause. Let's dive into the first three steps. Step 1. Determine if an epidemic is actually happened. You compare observed cases to the expected cases based on the past trend. So step 2, confirm diagnosis with laboratory testing. Do you need to test every single case? Of course, no. About 15 to 20% is usually enough. If a person has all signs and symptoms of a lab-confirmed case, you can count them as a case. Step 3, define a case, right? So the case definition should be simple and objective. For example, fever over 101 degree, diarrhea for more than 24 hours, and no other known cause. You may apply definition without bias to everyone. The Shigella outbreaks show this nicely. The epidemic curve has two lines: clinical cases and lab-confirmed cases. The clinical cases capture more people, but lab-confirmed cases are more specific. For the final analysis, they use lab-confirmed cases to avoid false positives. But for the early investigation, they use broader clinical definition to cast a wide net. Step 4. Orient the data by time, place, and person. This is descriptive epidemiology at its most powerful. First, time. You create an epidemic curve, cases on the y-axis, time on the x-axis. The shapes tell you everything. A sharp peak means common source. A slow rise means propagative spread. You can even estimate when the exposure happened by counting back one incubation period from the peak. Second, place. You make a spot map. The meso map from Cambodia is striking. You can see the cases clustered in a specific village. That tells health officials exactly where to send the vaccine. Don't waste resources on low-risk areas. Third, person. You look at age, sex, occupation, other demographics, right? In toxic shock outbreak, almost all cases were women. That was a huge clue. Without those three orientations, you're just guessing. With them, you start to see the pattern. Step 5, 6, and 7 are where you move from description to hypothesis. So step 5 determines who is at risk. This is often harder than it sounds, especially in large geographic areas. You might need a preliminary survey, right? Step 6, develop an explanatory hypothesis. This is often the hardest step. Everyone has an opinion: the media, the affected people, and the politicians. The job is to use descriptive data to rule out some hypotheses and generate others. Right? Step 7 is to compare hypotheses with established facts. Does it fit the known incubation period, the known mode of spread, population infected? Back to the toxic shock. Initial hypotheses include a virus or food poisoning, but the descriptive data showed almost all cases were menstruating women. That led to tampon hypothesis. Then they asked, does this fit the fact? The incubation period was short days, consistent with toxin, not an infection. The hypothesis held up. Then they tested with an analytic study. Step 8. Plan and execute a more systematic study. There's two main designs, retrospective cohort and case control. Here's how to choose. If you have a small, well-defined group, like a wedding reception, a church picnic, or a specific workplace, use retrospective cohort. You interview everyone, exposed, unexposed, calculate the attack rate. For example, at a wedding, you ask all 100 guests what they ate. You find that 90% of people who ate chicken salad got sick, but only 10% of people who didn't eat it got sick. That is strong evidence. If the outbreak is widespread, multi-state, affects thousands, then you use a case control study. You identify a sample of case and sample of healthy controls, then ask both groups about their exposures. It is efficient. The CDC data from 2,900 outbreak investigation show that 90% use cross-sectional study, 15% use case control, and only 5% use cohort. Some used multiple designs. The point here is you have to match the design to the situation. Step 9 and 10, report and control. The written report is not optional. It's like a hospital discharge summary. It documents everything. It serves as a basis for public health action. It records the team performance. It provides teaching materials. It protects you legally. So write it up. Then the control measure, the table 3-3 gives you 3 strategies. First, control the source. It means remove contaminated food, isolate affected patients. Second, interrupt transmission. It means hand washing, mosquito control. Third, modify and host responses that include immunization, prophylactic antibiotics. The hepatitis A daycare example is powerful. A single case in a child led to immunoglobulin shots for the entire group, children and staff. They acted before the lab confirmation because the epidemic evidence was sufficient. The organophosphate poisoning example is even more striking. The investigators identified contaminated bread as the source before the specific chemical was isolated in the lab. They pulled the bread from the store and prevented more cases. So you don't always need to wait for the perfect lab results. Outbreaks investigation have unique challenges. First, they're usually retrospective. You're asking people to remember what they ate or did days or weeks ago. Memories are imperfect, right? Second, you start with no hypothesis. In a typical research study, you have hypothesis before you collect data. In an outbreak, you collect data first, then generate hypothesis. That's backward from normal science. Third, their enormous time pressure. The public won't answer now. You might have to recommend control measures based on incomplete evidence. Fourth, you have to be responsive to the community while staying objective. The Legionnaire disease outbreak in 1976 is a classic example. At an American Legion convention in Philadelphia, people started getting severe pneumonia. Investigators had no idea what caused it. Descriptive data showed that all cases attended convention or visited the same hotel. So the hypothesis was something was in the hotel environment. They eventually traced it to the water system. The bacteria were growing in the air conditioning cooling towers. Control measure, cleaning the chlorination were implemented before the bacterium was even insulated. So that was the outbreak investigation under pressure. What kind of outbreaks are we actually seeing? The CDC compiled data on 2,900 investigations. 65% were infectious origin. 8% were non-infectious. 5% were environmental. 22% was unknown or others. So the majority are infectious. Where do they happen? Half in residential or community settings. 15% in hospital. 11% in schools. 10% in agricultural settings. 8% in workplaces. The rest in military bases and recreational settings. How are outbreaks detected? Data from 1999 to 2000 show that 31% were detected by health department, 25% by healthcare providers, 12% by infectious control practitioners, and only 5% by existing surveillance systems. That is important, right? Most outbreaks were found by frontline people, either doctors, nurses, infection control staff, not by computers. So training clinicians to recognize unusual patterns is crucial. Now let's talk about why cluster investigations are so difficult. I'm going to list 9 challenges. 1. Rare health events. Small number means low statistical power. 2. Vague cases definition. Someone says cancer cluster, but cancer is actually dozens of different diseases with different causes. 3. No clear population base. The demographic area of concern often doesn't match to the concentration or zip code. So you can't calculate the rate accurately. 4. Weak association. If there is a real effect, the relative risk is usually under 3, which is hard to detect. 5. Long induction period. Exposure might have happened 20 years ago and nobody remembers. 6. Multiple comparisons. If you look at enough disease, enough places, enough time period, you will find clusters by chance. 7. Low level, long-term exposures. The exposures are often too low to measure. 8. Intense publicity. Media pressure can be biased on the investigation. 9. Resource intensive. A full study takes months or years and can be costly. The CDC experience from 1961 to 1983 illustrate this. They investigate 108 reported cancer clusters, mostly leukemia and lymphoma. After all that work, no clear-cut etiology relation were established. That doesn't mean cluster never happened. It means proving causation is extremely hard. Occupational cluster investigation have some advantages, but also big challenges. So the advantages are you have a clear population at risk. You know the denominator. Exposures are often higher in the general population, so the effects are easier to detect. You can start with job classification before you know the specific exposure, and you often have comparable population for testing. But the challenge is also big. But there's also challenges. So most occupational carcinogens have been identified and controlled. Induction periods for occupational cancer are often 10 to 20 years, but many clusters are reported within 5 years of exposure. That is too soon. And many cancer types reported in cluster, for example, like breast cancers, hygiene disease, that is not typical considered as occupational. The NIOSH experience is telling. They investigate 61 workplace cancer clusters. Only 16 had a true excessive of cancer. Of those, only 5 were plausibly occupational. Most had no identified exposure or inefficient time for cancer to develop. That said, successful discoveries have been made, for example, vinyl chloride and liver cancer. So the cluster investigation can work, but they require rigorous follow-up. Statistical methods for cluster investigation are different because they are dealing with small numbers. Traditional statistics assume large sample size and defined populations. You can't use those methods for rare disease clusters. One common approach is to use the Poisson distribution, which is a mathematical function for rare events in time or space. The cell occupancy method divides the study area into sub-areas like census tracts and time into intervals. You count the case per cell and use a chi-square test to see if clusters are more than random. The limitation is that it assumes constant population density, which is rarely true. The interval approach, developed by Knox in 1964, is more sophisticated. You examine all possible pairs of cases. Each pair is classified as close or far in space and close or far in time. You calculate how many close pairs you will expect by chance. If you see more than expected, that suggests clustering. Knox's leukemia study is the classic example. He had 96 children with leukemia. There are 4,560 possible pairs. 25 pairs were close in space, 152 close in time. The expected number of close pairs was 0.83. He observed 5 close pairs that give a p-value less than 0.01, which is 1%. Statistically significant cluster. But remember, clustering does not tell you the cause. It just tells you that something is worth to investigating. Given how difficult cluster investigations are, we need a staged approach to avoid wasting resources. Stage 1, initial contact response. You talk to the person who reported the cluster. You log the contact. You notify your public information office. You provide assurance that you're taking it seriously. 50 to 60% of investigations close right here. A phone call resolves it. Stage 2, assessment. You verify diagnosis by reviewing medical records and pathology reports. You determine the geographic and temporal boundaries. You calculate the rate if possible. Another 20 to 30% close during this phase. Stage 3, major feasibility study. You review the literature, you consider study designs, you assess the social and political climate, you figure out what resources you will need. Stage 4, etiologic investigation. A full epidemiology study. Only about 5% of reported clusters reach this stage. Neutral criteria for a full investigation include at least 5 confirmed cases, a potentially large relative risk, which is over 8, and good estimates of personal exposure. The CDC's experience matches this. Of 41 reported cancer clusters in 1 year, 56% revolved with a phone call, and only 7% become a full study. All right, let me wrap up here with some key takeaways. Outbreak investigations have been much more scientifically fruitful than cluster investigation. Outbreaks are naturally experiments. They give us clear before and after comparison. The methods are well established. We can often identify the cause and implement control measures quickly. Cluster investigations are harder. They rarely lead to new etiologic discoveries. But here are crucial points. Public health has an obligation to respond. If we ignore a reported cluster, even if we think it's nothing, the community will perceive a cover-up. So that erodes trust. We respond quickly, systematically, and compassionately. Cluster investigation also give us opportunities. First, public education. Use the teachable moment to explain the rates, risk factors, and preventions. Second, screening. If there is effective screening for the disease in question, mobilize resources. Third, risk communication. Work with media to present meaningful information. Fourth, surveillance. High-quality surveillance systems are essential for detecting real problems. Outbreaks and cluster investigation combine science, communication, and action. They require sound epidemiologic method, rapid response, and the ability to balance scientific certainty with public demand for answers. Even when a cluster turns out to be random variation, how we respond matters. Thank you.